Thank you for coming to my talk. I bet you're all thinking that I know some pretty important people to be presenting on a not graphics topic, and, well, I guess you'd be right. Um, pretty tough act to follow. I'll do my best to be entertaining. For those of you who don't know, was a graphics developer for the Intel graphics stack starting in 2010. Sometime last year, like some cool people before me, Keith, Eric, and Christian, left Intel graphics to do other things. So one of those other things, which I am actually only doing in my free time now, but I was paid for, is looking at FPGAs and trying to make a more open stack for FPGAs. I assume most of the people in the room are kind of familiar with FPGAs to the extent that maybe they played with them in school a little bit or are familiar with Chameleon. So I would really like to spend some time talking about, sorry, one second, am I here? Yeah. Talking about what FPGAs actually are and what the tools are all about. So I assume most people are familiar with this meme. It's one of my favorites. I learned recently that this father and son duo actually had a falling out after this and didn't talk for several years. So that was kind of a bummer. But this is a conversation I have with myself as a representative of a company that manufactures FPGAs. And I'm saying to myself, well, why aren't we better, and how do we get better? And generally speaking, my assertion here is that the ecosystem is not ready to get better until they're more open. Part of the reason I wanted to speak here is because I also see a lot of similarities to graphics from 20 years ago or so, and I'm really hoping to get some support. Again, like I said, this is kind of my free time thing, so it could be your free time thing too if you want it to be. Quick agenda. So we're going to talk about what FPGAs are, what the tools are. We're going to talk about how they're being used. Specifically, there's a little bit of an Intel slant to this, mostly because that was where I was able to get a majority of my information. And then I'm gonna wrap up just to talk about how I see the similarities and dissimilarities, and where I think the community can really use some help. So let's talk about lookup tables, which was a nice transition also from Alyssa's talk. I assume a lot of you are familiar with the term lookup table, display folks in particular, and what you just heard. So I wanted to really drill down and we're going to build maybe a mini theoretical FPGA. And to do so, you need a lookup table. And in our case here, we're using an SRAM with 6 transistors. This is not my background, so I'm going to hand wave a little bit. And you have 3 muxes. And I assure you, no matter the process, you will have enough logic gates to make a mux. It might not be exactly what you see here, but underlying those are transistors as well, and you can do this. So generally, you'll have some kind of static storage. I'm going to try. I was hoping to have a pointer. That's this thing. And those are basically just sitting there. And then you have 2 inputs, which are going to drive the output, and this will make a little more sense in a second, for the Boolean logic or the Boolean expression. So let's actually do something with that. So we just had the same diagram as before. And now all of a sudden we can make an XNOR gate, which is not something you typically get on any processes, by populating your SRAMs with, with these values, 1, 0, 0, 1. And then if you kind of follow the logic, okay, you pick 0, 0 for A and 0 for B, and you get this thing, it's a 1. And you can kind of go all the way through. And so now, with 3 muxes and some SRAM, you've implemented an XNOR gate. Let's see, maybe a question for the room. Can anyone tell me what might be different with a lookup table-based XNOR versus an actual exclusive NOR gate? Slower, yes, very good. There's delay, because all these muxes are driven by a clock, and so for every layer of mux, you're potentially adding delay. Now, I should say, the FPGA vendors have gotten good at this, and so this is sort of a simplified version, and the delay would actually be much less. So for instance, if you had a 4-input lookup table, you wouldn't expect a 4-clock delay there, but generally, that's sort of the problem. So you get the goodness of like, hey, I get to implement whatever logic gate I want, or maybe a non-existent logic gate, but you get the added delay. So let's take a little bit further. So LUTs are cool because you can combine them together and make bigger LUTs. And with bigger LUTs, you can get more complicated Boolean logic. So in the example here, I took my two LUTs that I had earlier, and I muxed them together, and now you have a 3-input LUT where the new input is driving which LUT you're using. And I tried to color code sort of the corresponding Boolean logic, and the Y here is what you would input in the SRAM. So these 4 would be for the first 2-input LUT, and these 4 would be for the second 2-input LUT. And in this example, we've made the Boolean expression. Oh, sorry, my mouse wasn't there, was it? We've made the Boolean expression A and B or C, which, again, kind of cool. You get this one block that's implementing combinational logic, which you could do in an ASIC, but it requires a little bit of extra work. And so it happens, and I'll describe in a second, you have more and more of these things, and so you can have kind of custom combinational logic throughout your FPGA, which is why people like them, I think. So as I was saying, most FPGAs aren't really just lookup tables. They're a lot more than that. You'll have flip-flops and adders and carries, and those carry chains. And those carry chains are generally meant to make speedier arithmetic because as the as the units are laid out on the chip, you might not have direct access between any two logic cells. So here's sort of a theoretical diagram where you have these blue things represent several LUTs and flip-flops and adders, and they're throughout the chip spread out. And then there's this meshed routing network where you can kind of direct the output from one of these. I call them labs, which is Intel's terminology. Logic, I forget what it stands for. LAB, PLB, and CLB are like the Altera, Xilinx, and Lattice terminology. And ALM, LE, and Slice are similarly, or I guess LE is Lattice, so it's Altera, Lattice, Xilinx.
Logical array block.
Logical array block, thank you. Anyway, they're routed as such, and so you can kind of begin to see, like, hey, maybe if I have stuff happening right here, and I put some stuff over here, maybe it's not going to be super fast to get the output from the top left one to the bottom right one. Okay, so there's more, right? Like, what we've just done is incredibly useful because you can't actually drive any signals or sample any signals on the output. So a lot of times, these FPGAs will be connected to a series of GPIOs around the chip or other inputs and outputs. And in this case, just for an example, I've thrown a bunch of IOs all around. And so maybe you can say, where is it? Dang, oh, there we go. Okay, we're going to have our inputs up here, and we're going to do some stuff all throughout, and our outputs are over here. And these are just wired to whatever FPGA board you're going to have. But it gets a lot more interesting than that nowadays, because FPGAs no longer are just these programmable logic cells. And I should step back and say, with a lookup table, you can implement memory and all sorts of things. It's you hear about these RISC-V CPUs that are implemented entirely with these logic cells, and you can do that, but those are typically slower. And what is nice is these days you're getting what are called hard CPUs, which typically are ARM, that are just on the FPGA. And if you want to use a CPU in your design, you kind of make sure it's all wired up correctly in your routing network, and you're good to go. And you might have memories, typically each of the LUTs. I mean, I want to hand wave a little bit because it's not worth the details, but you might have some memory and DSPs and so on. And so a lot of these higher-end FPGAs will combine all these hard IPs in addition to having the programmability. By the way, if anybody wants to stop me for questions, feel free. So, the name of my talk is Everything That's Wrong with FPGAs. What's wrong with all that? It was rhetorical. Don't worry about it. I got you covered. The programmable nature is both a blessing and a curse. You're able to program it, but typically that means you get things slower. The effect really has to do, generally when things are more programmable, they're slower. And that's typically just a nature of the number of transistors and maybe delay in the clocks. The thing that really bothers me is, as I was kind of describing this theoretical FPGA, is you might have noticed that it really gives an opportunity for the hardware vendors to do things incredibly different. So both routing and what the logic cells look like and how many RAMs there are and adders and what the carry chains are connected to. And that makes it really difficult to have a single stack and sort of abstract concept of what an FPGA is, more so than you might think on the surface. And furthermore, the standards for the HDLs, which the primary ones are Verilog and VHDL, are not nearly as stern as I would say graphics standards are. So you don't have the same kind of conformance test suites. Different synthesis, or I should say different EDA tools will work differently and will accept different inputs and extensions. It's a little bit like, I guess, GCC versus LLVM in that sense, or maybe GCC and a proprietary compiler would be a better comparison. And what ends up happening is, if you're a designer or an integrator, you end up taking the libraries from the vendor, so maybe some sort of gigabit Ethernet IP, for instance, and you just use that, or a memory controller, and you just use that. And then once you've done that and you've spent the time to integrate it, you're now locked in. It's a lot of money and time to go and say, hey, I just did all this with Xilinx, and now I want to use Lattice. Most people can't afford to do that. And so the third bullet here, again, the hardware differs drastically, and I just wanted to point out, even though it differs, I believe there's some area for improvement on trying to make a description of the actual floor plan of the FPGA so that you could come up with, if you want to think of it as like the nerve for FPGAs, maybe there's some intermediate representation that you can standardize. And I'm going to talk a little bit more about that too. So we're going to go to tools. Oops. When I say tools, I want to be specific. This is sort of the terminology that they use in FPGAs, but it's a lot closer to what you might call a user space driver. It's not like instrumentation or debuggers or anything like that. So quickly, let's go over the current landscape. In FPGAs, vendor tools are the norm. If you are doing anything in production, and don't hate me, but you are using proprietary vendor tools. I've listed 3 here. That's, again, Altera, Xilinx, and Lattice. And typically, you'll use those, and you'll use either these cells, which are containing the IPs you want to implement, or you might be designing something from scratch, but it'll be the entire tool chain. So that's, and I'm going to give some details here later, but just generally synthesis and doing your timing and place and route and creating the actual bit streams that are going to go on the FPGAs. Now, I do want to point out something that Xilinx is doing. I wouldn't say it's open source, but it's very friendly to open source, where they're allowing you to use third-party tools to actually do place and route. And again, I don't necessarily expect you to know what that means just yet, but they're allowing these third-party tools to kind of work into internal parts of their tool chain that will allow more flexibility for, open source tools. There are third-party tools as well that are proprietary. Those will typically take care of the front end of the process. Cadence, Mentor, and Synopsys being the big 3. The way that the process works is there's sort of this synthesis at the front end that, while it does need to know the underlying technologies that are on the FPGA, you can do it generally well enough that there is an ecosystem available for that. And on this next bullet, open source tools, that's kind of where they're targeting. So right now, there's an incredible project, I guess it's an entire flow actually, called Yosis. And you guys, I highly recommend you go look at the YouTube videos. They do a ton of presentations, and it's incredible, the work that they've done. But their main platform is Lattice. So they've managed to reverse engineer to lattice FPGAs to the extent that you can run some pretty complex designs on them with an entirely open tool chain. And I'll go over those projects too a little bit later. And finally, there are kernel interfaces now to let you program these FPGAs. And this is where I really wanted to come in and talk to you guys today, because this is where things are becoming really terrible, in my opinion. There's one interface that's being pushed by Intel called DFL, and some of the acronyms I should mention have changed, so later on there might be some things where if you are familiar with it, I might use the wrong acronym. So DFL is a way in which you as an FPGA vendor can ship an FPGA where you list sort of general properties of your FPGA if you wanted to use it as an accelerator. And there's kernel drivers for this to read it out and expose it to user space. And that's all well and good. The real problem is really only Intel uses it. And as far as I know, and I have to be honest, I haven't been paying too much attention recently, but as far as I know, nobody else is interested in picking it up. So you have this like giant framework in drivers FPGA, DFL star, which is really only serving one vendor. They wrap that with something called OPAE, the Open Programmable Acceleration Engine. And I think I have a slide on it later, but generally you can kind of think of it as like DFL is DRM and OPAE is libDRM. It's a pretty thin wrapper that allows you to actually access the interfaces. And then you get this slew of specific FPGA interfaces, which typically allow you to either write an entire FPGA image, read it, erase it, so on. And so the directory is a bit of a nightmare, I think. Oops. There we go. Okay, but let's get to the details of the tooling a little bit. Sorry for the ice chewing. So a typical FPGA flow would be you start with a high-level description language, and that is typically Verilog or System Verilog if you're fancy. That gets converted to a netlist, which then gets routed, and I will go into details. You get a bit stream out of that, and that goes into your FPGA. It's quite a complex series of problems. Synthesis is NP complete, circuit minimization and technology mapping, and an actual place and route in the real world is NP hard. So I think you can constrain the problem a little bit, and I think it's technically NP complete, but practically it's NP hard. So there's quite a bit of challenges in here for the compiler folks in the room who are getting tired of shader compilers. The rest of the stuff is actually trivial, which is kind of cool. And I guess I can go over, I better not. I can go over a description of these things a little bit better later on. So here's an example using the LUT2. I suspect you might not be able to read it. In the upper left corner, let me try and do this, is really simple Verilog to implement an AND gate. As you might expect, it takes two inputs, and you AND it, and you get an output. In the bottom left corner, you have, so this is Yosys's, it's called RTLIL. It's their intermediate language, and it converts, it's exactly what it sounds like. It's an intermediate language. That, in this case, is quite simple. Where is it? It's telling us that there's a LUT, and it has a width of 2. I can't really find my mouse over there, but you can take my word for it. There's a generic synthesis script in Yosys that allows you to do this and say, hey, I have a LUT, I have a 2-LUT FPGA or underlying device, and please synthesize for that. So if you didn't do this by default, you might end up with AND gates. I forget what the default is. But if you were to do this for a real device, it would try and synthesize to the actual underlying device. So you might see this very complicated thing that represents the logic cell. And on the right, you have a JSON representation of the netlist, which you can see there are ports and cells. And for me, this was unfamiliar territory, but just generally, you can think of it as a graph of logic and how they're connected. Okay, cool. So we did a LUT3 before, right? So let's actually kind of try and make sense of all this. So if you have our same Boolean expression A and B or C with a LUT3, dang it, there we go, right there. You can see the intermediate representation again down here. And if you look, there are some fixed bits for the LUT, and it's a width of 3. And if you sort of transpose the previous truth table that we have, all of a sudden you see, hey, there's 1, 1, 1, 1, 1, 0, 0, 0, which in the intermediate representation is exactly what we had. So this is just showing you what the SRAM state is of the LUT in a general sense. Now, I'll remind you again, the LUT3 that we developed is not at all as complex as the real one. So this is kind of like just so you just so you get it. Well, then it becomes time to place and route, and this is really where the complexity and the secret sauce is for most of these vendors. So the way that the vendors differentiate themselves is they figure out for given workloads how to put all the right combinational logic in a fast path. So maybe they'll know, okay, we're going to do a lot of inference on this thing, and so you need so many logic cells, and they need to be in this fast path in order to get the best throughput. But generally, place and route is fairly straightforward. Placing is finding locations for your logic on the actual chip, and that can be challenging sometimes. As I mentioned here, you do have timing constraints, and you do have to make it fit. And then with these fancier FPGAs, you have to figure out how to utilize the hard IPs. So a lot of the open tool chain work today doesn't really take advantage of the hard IPs, which make the actually more complex designs look rather bad in comparison. Routing is the second part of the problem, which is where you're actually figuring out how to connect things. And in our trivial example, as you can see, I've just pretended that we're outputting I didn't even provide inputs, but we're just taking the output of the A and B or C and routing it out to some GPIOs. And the way that the synthesis tools work, because there's no optimal solution for all things, is typically you can specify whether you want to have the smallest area, the highest performance, which would be typically the shortest distance between the LUTs, or if you want to optimize for power. And again, I'd like to point out the information of the floor plan and how things are tied together is what's not published, and most of the fuzzing efforts that take place today are figuring this out. The synthesis part of things, what the LUTs are made of, the size of the LUT and what's in an ALM and so on, that's actually in public documentation. And that's to support the third-party EDA tools. Bitstream assembly is really straightforward, actually. I mean, it's what you'd expect. If you know what the LUT programming is and how to program the actual routing in the fabric, some bits go in some part representing the LUT, some bits go in the routing information, and you're good to go. There are some special cases. A lot of, especially the higher-end FPGAs, will support encryption of the bit streams, which may or may not be a good thing in your opinion, and also compression, which is a good thing because some of these bit streams can be quite large and it can be quite slow. There's some cool stuff happening where you might upload part of the design, which is your decompression, and then you'll actually upload the rest of your design compressed. So there's some fanciness here that can happen, but generally it's sort of a pretty linear translation from your abstract place and route information to bitstream assembly. And finally, there's programming, which is also pretty straightforward. Typically, or most of these platforms, you'll have a JTAG interface, and really the only choice, which will be either a GPIO or a jumper on the board, will be if you're going to update the live flash image, so what you have currently running, which gets reset every time you power cycle, or if you put it into flash or some sort of non-volatile RAM. All these things, not all these things, but most of them, when they come out of reset, will check if I'm supposed to read my data out of NVRAM, and if they do, or if they're supposed to, they'll just do that. The most challenging part, or the part that I think open source has been slow to catch up on, is what's called partial reconfiguration. So instead of wiping out your entire FPGA image, you can actually select parts of your FPGA image that you want to reprogram. This is kind of useful, as you'll see in a second, around some of the accelerator use cases. Cool. What's wrong with that? I don't know. I think there's a lot of things wrong with that personally. But I wrote it down. So the tools are proprietary, which I think most of the people in the room probably think are bad. Not everybody does, by the way, but most of the people in the room think they're bad. And they differ so drastically by the hardware vendor that if you want to go from one FPGA to another, I said it can take days to get up and running because I didn't want to get in trouble, but it took me a really long time to get Quartus, which is Intel Altera's tools, up and running. It was not a good experience at all. And to get Diamond running, which I probably should talk even less about because I don't work for Lattice, well, that got up and running really fast, and then it broke, and I couldn't get them to respond to my emails to help me fix it. So I can't even run Diamond anymore, even though I have a year-long license. But that was sort of neither here nor there. So the second one is related to that, which is the license server. So all these things require you to run a license server, which is a binary, and you have no idea what's on there. And that is really uncomfortable, I think, especially if you're in a corporate environment where you would think that your IT department would really want to lock down exactly what you're running. But people do it, and that's how it works. And for these larger companies, they get a site license, which is kind of a little bit better because you can just point it to a server, and maybe they can, I don't know, sandbox it or whatever, but it's not great. If you have any problems at all, you have to contact their customer support. Obviously, you can't, you can strace if you want, but my experience hasn't been very good. And customer support, I guess, obviously varies by vendor, but I would expect, unless you're a big customer, you're not going to get the fastest support. And I've heard stories that aren't mine, so I won't recount. But if you kind of look around the web, you'll hear some pretty terrifying things. The cost of entry for using these tools. So the real thing that irritates me or gets to me sometimes is the way that there's almost an addictive nature to this. So the way that students get accustomed to tools is these hardware vendors will send free FPGAs to universities, and they'll say, hey, here's a free license, university. Go run our tools and learn how to use these FPGAs. Well, that's all well and good, because when they graduate, they're like, I know how to use Quartus. I'm going to use Quartus. And that is not great. And so you end up with a lot of people who don't necessarily know how to actually use the tools that they might have been hired for, because maybe we're a Xilinx shop and we don't use Quartus. And so you end up with a lot of people purchasing IP blocks from the vendor, which isn't inherently a bad thing, but it certainly limits your ability to do custom designs, and it certainly limits your ability to differentiate yourself if you're trying to make any sort of FPGA as a product. We're up to this bullet here. Customers are unable to improve or debug the tool flow. That one should be pretty obvious. The way that you do any sort of automation or any sort of improvements to your design in an automated fashion requires TCL, and the interfaces are, well, okay, this is subjective. I think the interfaces are bad. They are objectively not well documented. So that's not good, huh? And I don't think my presentation actually covered everything that's wrong. What do you think about that? So how are the tools used? I want to talk about market size real quick, because I'm going to go into marketing and make more money. The interesting thing about the graph isn't the numbers. So it is in billions on the left, on the y-axis. And this data is from Wikipedia, so you know it's good. And when you go and dig into it, you see that, wow, actually this is from some marketing report, and these guys said it was a $2.5 billion industry. And then you look at someone else's data, and they're like, it's a $6 billion industry. And then you look at someone else's data, and it's, whatever. So the point I want you to take out of this is the curve of the graph, which of all the marketing data I was able to get, did seem to stay fairly consistent. And what's cool to me, or what's interesting to me, I think, is you look at all these people who are innovating FPGAs. So Xilinx started in '84, and you have Actel, which got acquired by Microsemi, and you have Altera in the early '90s, and QuickLogic in the late '80s. And Lucent actually spun off what Lattice now has today for their FPGA solution. But if you look, and I'm trying to find my mouse, so I'm just going to describe it. If you look, the FPGA market wasn't actually growing when these people were creating their FPGAs. So I think there's two things to take away here. The reason the FPGA market is interesting now is one, transistor density has improved, and you can actually have kind of FPGAs with a lot of programmability. But two, we've actually come across problems where FPGAs might be interesting. And if you look at that 2010 threshold, this is sort of when like AI as a everything took over, and inference and neural networks and so on. So I believe that the market's actually going to get better, or bigger, I should say, but not because there's new technology per se, just because there's new usages for it. Okay, so we're going to talk a little bit about how FPGAs are used. The traditional thing, which is sometimes called the vertical FPGA, is exactly what probably most of you think of when you think of an FPGA. Someone goes into a room, they have an FPGA on their desk, they're trying to get all the RTL for it. It has a specific function, maybe it has multiple functions, but generally it's just this offload card of some sort. And there's a few reasons you might want to do that. I don't want anybody to quote me on this number. This is from an Altera training, which I think is public, so I can say that. But if you're shipping in low volume, there is a point, if the volume's low enough, where it doesn't make sense to do a custom ASIC. And so FPGAs might be the right solution for you. And in that training, it said it's around 3 million units where that's the case. But that sounds wrong to me. I'm just telling you that's what I heard. There are definitely use cases for volatile specs. So when I started as an engineer, I was working with media a lot, and a lot of the MPEG-4 standards hadn't been solidified. And so if you had any sort of hardware transcoders or anything like that, a lot of them had FPGAs in them, because as the spec would change, they can update the image remotely, and or you could do it as the customer, and bing bang boom, you're good to go. So that's actually still a pretty valid use case. The other is you can't wait for ASIC turnaround. This is sort of like, I have a customer who is going to want new silicon tomorrow, and I'm not going to be able to get a custom ASIC for that. I don't think that's super common. And probably the final common one is to simulate your ASIC before RTL freeze. So you can typically run in at least the tens of megahertz for complex designs, and if you want to validate your ASIC in any way, FPGA is actually a good option. And a lot of people in the room, I assume, who work on graphics, when they're using their emulation environments, really those are oftentimes backed by an FPGA, and that's why you do that. I won't spend too much time here, but this is what the flow might look like. You have an FPGA on your desk. You're developing the entire stack either by acquiring IP assets from somewhere or writing the code yourself, and you're putting all the glue together. And so when you're ready to go, you have your HDL. It gets synthesized. You have a bit stream, and it ends up on the FPGA, typically in the flash. And then you ship your FPGA. Good to go. Oops. There's something called high-level synthesis. Some people are interested in this. Actually, it's been an area of research for the last at least dozen years, and it's been growing quite a bit, although I wouldn't say necessarily that it's popular. This allows you, using a high-level software language that probably most people in the room are more accustomed to create your designs. I think all the major vendors have solutions for this. I've heard rumblings of some companies working on separate solutions for this. But generally, this is just the same thing as what we described before, except maybe you'll have C++ instead of writing Verilog. Okay, the FPGA. This is where Intel specifically has invested a lot of money. The idea is there's an FPGA somewhere, and it helps you do things fast. And there's kind of two main ways to get to this. The first is you have some sort of runtime, and I've listed 3 of them. OpenVINO and DLA are Intel specific. Well, they're open, but it's primarily Intel. OpenStack Cyborg, which is obviously OpenStack, does use OPAE as a backend, and the Kubernetes plugin also uses OPAE as a backend. But generally, what these are doing is it's creating an interface for you to use parts of the FPGA as an accelerator, and I'll show you a little bit on the next slide. But also cloud service providers are now providing raw access to FPGAs as well. So Microsoft and Amazon both, and there's probably others, I mean, this was sort of a few months ago, allow you access to FPGAs in a virtualized way. And so here are the kind of two cases that I just described. The top one being you've written an application and you have some runtime, it goes through OPAE, and it ends up on the card. This is where I was talking about terminology earlier. So the AFU thing is a accelerator functional unit, I believe. And the way that this works is basically these vendors will divide the card up into blocks, which you can use as accelerators. So think like there's a chunk of the silicon, and I can upload a gzip compressor if I wanted to, and it'll go really fast. And so what the runtime will do is it'll say, oh, your application wants to zip something, so I'm going to go and upload that AFU, and I know exactly how it interfaces, so I can upload all your data that needs to be compressed and take all the data off that you need to do with the compressed data. And this is kind of where I think there's some overlap also in the GPU community in terms of memory management and your sort of execution management, because fundamentally you're taking buffers and putting them on the card, and you're working on them and taking them off the card. Maybe not display, but off the card. And the bottom guy represents what I was talking about earlier in terms of using. This is using maybe a different kind of high-level runtime. So, and this is one area where if the Khronos folks in the room want to tell me a little bit about SYCL, I'd be interested. But maybe you have some API that's capable of translating whatever acceleration you want to do. Typically, these days, they're going into CL, and then you have a CL to HDL conversion, and then you go through your normal flow. Now, the bottom one could also work with that top one, so you can use SYCL to create an acceleration unit and then go through the runtime and have that on there. But I don't think anybody's actually doing that today. That's the FPGA flow. And then there's the FPGA flow. This is not as common, and I was trying to find other people who are doing this. But Microsoft does have a working. It's more than a demo, but they do have something that's demonstrating exactly what the quote says. So they've basically created their own NPU, and it has its own instruction set, and it apparently works really well, or at least they claim it does. I believe them. They do? What's it called? Alveo. Oh, well. Sorry, guys. Sorry. I should have been up to date. My bad. The FPGA, or whichever one flow, is an interesting one. So you make your custom design in Verilog, or whatever language, and you synthesize that, and it's running on your FPGA. And one of the, I forget if I put this in the what's wrong with that slide, one of the issues with that today is at least some of the information I have is doing the synthesis for an FPGA for these custom NPUs can take on the order of a week. So if you want to update something, it can take a really long time, and so you better have a lot of data. And so one of the areas where I want to, again, advocate for Yosys is, while it might not make the most optimal designs, so maybe this isn't a good example, it does do so much faster. So you can kind of prototype things really quickly. But generally you have, generally you have your NPU, and then sometime later you have your C application or whatever, and you've got your custom compiler that knows about the NPU, and it can go and generate whatever offload kind of AI thing you want to do. I think there's a lot of potential here, and I think I think I do talk about it. Yeah, next slide, sorry. So what's wrong with that? I don't know. The FPGA market's pretty small, actually, even though I think I said it'll be 10 billion in 2022. That's not huge, And in terms of number of units shipped, it's also not huge. And it's not a very accessible market. And what's kind of worse is you can get a dev kit really cheap, but the difference in complexity between a dev kit and a high-end FPGA is like night and day. So there's not really a lot that kind of a regular person or an open source consulting company can do without spending a ton of money. As I kind of said earlier, the vertical FPGA developers, they went to school and they learned whatever because whatever company shipped them the free FPGAs, and they don't want to switch, right? They can get their job done. They've learned the nuances of the tool. Maybe they've learned to work around the bugs. It works for them, and they have no interest in improving it, or at least generally that's the feedback I've gotten. The accelerator flows tend to rely heavily on CL, and this is really not optimal for several reasons. Aside from the fact that it's slower, well, I think the room knows kind of why OpenCL may not be the best for this. OPAE is great. I think Intel, and by the way, I should mention that a lot of the people who were responsible for this have since left Intel, but it's the right idea. It's trying to standardize an interface to use FPGAs more generally. The problem is that the interface itself is relying on proprietary stuff. So it's expected that you're using these proprietary acceleration functions. It's expected that you have some shim on the FPGA side to pull data over PCI Express or whatever. It's not, it wasn't, I guess to give maybe Dave Airley a compliment, it wasn't enforced early on that you needed to have open source as a user space. And that's led to nobody having open source as a user space. FPGA is really resource intensive, so that last one I talked about, you need serious hardware engineers to make an MPU, and you need serious time to synthesize it and update it and find out like, hey, maybe I change this one bit in the ISA and things go faster. Not a lot of people can afford to do that. I think one of the ways in which that can be improved is if someone or some company wanted to do sort of reference designs for this, and maybe it's not the most optimal, but you can put it out there and say, hey, you can do an MPU with this, and you can go and figure out how to modify your MMU and make it faster. I don't know. I think that's one area that could potentially be quite interesting. The high-level synthesis hasn't really taken off. I don't know necessarily that it's for any specific reason. Again, I think there's a lot of momentum in the old way of doing things. I think the tool chains haven't worked very well. But more generally, it is what it is. And yeah, the compilers did the proprietary thing too. This is more of a comparison. There's a lot of people I talk to who tell me that the open source, this will get you going, that tell me the open source community isn't capable of writing a full FPGA toolchain. They say it's too hard of a problem. I was even told, well, maybe I shouldn't say that. But there's a lot of misinformation. I'll say it that way. There's a lot of misinformation where genuinely, and it's, you can fault someone for being ignorant, but they're not malicious. Genuinely, people believe that Intel's compiler is better and makes a lot of money. And I believe that's probably true in ARM. I can't speak to it. And so when you talk to them and you say, hey, people actually use GCC and LLVM in production and they prefer it, they think you're either lying or don't know what you're talking about. So there's a lot of misinformation that you need to try and break down, because these aren't software people that you're talking to, and they've been in a relatively established way of doing things since the early to mid 80s, and nobody's really shaken it up. And I failed to shake it up myself. Okay, I think we can wrap up now with what I'm going to say are the comparisons and the lack of comparisons. So generally, compared to a GPU, you have a dense set of transistors, and it's more powerful and focused on whatever it is you might want to do. That's pretty cool. There are new markets, and they're growing all the time. GPUs too, right? It's used for things today that we wouldn't have thought of many years ago. Similarly, there are a limited set of vendors. I think there's about 8 or 9 people actually producing FPGAs, but Xilinx and Altera own between 70 and 80% of the market, and that hasn't really changed. The Lattice FPGAs have a real adoption with the open source community and the enthusiasts, because of course they have the open tool chain, but I mean, people buying a $60 ECP5 aren't going to make a dent in the overall market share. Lots of proprietary software. I mean, anywhere you go, the tools for timing analysis and synthesis, the go-to is proprietary. And even like if you go to the web and kind of look at whatever forum or mailing list, it's all questions and answers around the proprietary tools, not what can we do to make this better. There aren't really, aside from the folks working on Yosis, there aren't really a lot of people who are trying to do anything but make a product. There is a lack of good documentation, so this is sort of unfair. I think both Xilinx and Altera do have quite good documentation, but it's only for a certain aspect of the overall flow. The majority of what needs to be done today is reverse engineering, and where I got stuck at Intel is I was told, okay, well, maybe we can't open the docs, and I'm not allowed to reverse engineer my own company's products, so what do you do? So even if you have people in these companies who want to make things better, their hands are often tied. A lot of binary blob drivers, like I said, I mean, these AFUs, these accelerators, they are typically just made by the vendor, given to the customer, and people don't even really know how they work. Pretty much everything that's running on your FPGA is a blob. There is a vibrant reverse engineering community. There are several projects that are working, hold on, I might have that on a later slide. No. There are several projects that are working on reverse engineering a lot of the bit streams and the floor plans. Project Trellis is the most famous one. That's lattices, and there's a few different ones for the different Xilinx generations. There's one that's smaller that's happening for Altera, which if you want to know more about, you can come talk to me. I don't work on it. But there is a lot of academic interest in this, which is kind of driving, I think, improvements. Did I run over time? Okay. There's and then like I mentioned earlier, DFL and OPAE, you kind of have a lot of similarity there. It's just the user space side wasn't pressured to do better. Where are we dissimilar? So, oh, just kidding. Where are we dissimilar? There aren't strict standards, as I was saying earlier. You can run a conformance test in graphics land and know roughly if your driver, I mean, I think a lot of people might not think the graphics standards are potentially as good as they could be, and the test suites aren't as good as they could be, but I assure you that it's better than what exists in FPGAs, or I should say in descriptor languages for hardware descriptor languages. There's we should have something like Mesa in FPGA land, and I think Yosis and XPNR, which is the place and route framework, should be that. There should be consensus from people who know the different hardwares, coming up with something that makes sense for all the FPGAs, at least in terms of a front end, and you will then, I think, see a lot of progress happen. And it's not that people are like, oh, we should do open source tools, but it's not Yosis. It's just that there aren't a lot of people that are kind of coming together. And there are some. It would be unfair to say there aren't, but there are. It needs more people. And we need the piglet. I mean, we need something that you can run and run it quick and make sure that you're able to, your tool chain's able to generate a design that will work. The kernel interfaces are in their infancy. I mean, graphics interfaces are fairly well established by now, and so you're getting quite a bit of churn in there. The interfaces themselves are driven by Intel, which isn't necessarily bad per se. I mean, it's fine if one company wants to be the leader, but it doesn't seem to me like people are really following. There's standardized way to put non-standard. I don't know what I meant by that. Oh, yeah. So I guess the question I'm asking is if you want to ship an FPGA as an accelerator, should the interface for that accelerator, if it's the same functionality, should actually differ by vendor? So I use the gzip example as sort of a trivial one, but gzip is gzip, and it should be that if you want to have a more open ecosystem, those interfaces for the accelerators are actually well defined, and you can say, okay, we're going to get this accelerator on there, and as user space, I know how I can make use of that. That's sort of the step below having an open source implementation of the accelerator. There's lots of emphasis going on right now about opening the interface to the device, but very little emphasis on getting to the actual software that's running on the device. And I did use the word software there intentionally, and I think there is a lot of argument between people about whether or not that's software. But so generally, though, what's running on the device has been a black box, and it continues to be a black box, and people are much more concerned with how do you get those black boxes onto the FPGA. The issue that I ran into personally, which is maybe where the Google folks in the room can help, is I was told basically no big customers are asking for open tools, so why should we bother? And that's fair. I mean, if you're selling silicon and none of your big customers care, why should you? It's a fair point. But if you have products that are using FPGAs and I heard anecdotally SpaceX, for instance, had a really hard time with their Xilinx FPGAs, and they were unable to debug them. And having the ability to do these things for you making a product will help. And so, if you have a contract with one of these FPGA vendors, you should be asking for better tools and open tools. Okay, so how can we learn from the mistakes? I think this is basically reiterating what I've already said. I'd really like to see an enforced policy for having a more open user space on these tools before patches will be accepted into FPGA drivers. Get unit testing in there. Don't allow interfaces that will only work for one type of hardware. I mean, these are all things that you guys should be pretty well familiar with. So I'm not going to harp on that too much. But number 8's the one I like, which is, don't assume because it's open source and not driven by a company that we can't solve this problem. Because I assure you a lot of people in the room are smarter than the people that I've been talking to. Or at least less ignorant. So what can you do? Use the tools. Do something cool. There's an adage along the lines of FPGAs are about as performant as 2 generations process ago. Again, that's hand-wavy, but what that means is the current line of Altera FPGAs, for instance, you should be able to implement Sandy Bridge if you wanted to. So go do that. Find the bugs. Make it work with the open tools. Do something that interests you. I've gotten several commits in which were very trivial, but they made my life easier to use the tools. It's a very open community, and this wasn't meant to be a rah-rah Yosis talk, by the way, but it is something that people should really look into. Improve the P&R efforts. So this really comes down to reverse engineering. If that's your jam, there's a lot of work going on for a lot of different platforms, and if you want to come talk to me or email me after, if you have trouble finding it, they're not super hard to find on the internet, but if you do have trouble, come ask me know. If you're a standards guy, figure out how we can if you're a standards person, figure out how we can make standards so that tools can access these things more easily. Maybe there aren't answers to this. I don't know, but I'm sure that someone who is familiar with kind of writing standards can do something better than nothing. And finally, if you want to kind of make sure that things are going in the right direction on the kernel, there is a separate mailing list. It's pretty low traffic, so even if you're just kind of tangentially interested, it's not a bad place to go. And I believe with that, I will say one thing just for like the people who did all the ice storm, anybody who had an ice storm thing. So there was a previous place and route tool called Arachne, and that's been replaced by NextPNR. So don't use the old thing if you want to play around with this stuff. And that's my talk. Thank you everybody for hopefully paying attention. Any questions? Maybe raise your hand if you're playing. Okay.
Hi. So we work at Collaborate. We work with Xilinx, who are our customer, on the more SoC side, like GStreamer and stuff. But they have a whole open source stack on the how to get bit streams onto the FPGA. So it's very similar in a way to what the GPU people have. Like, you have a proprietary thing to generate a bit stream, and then you have an open source but device specific. So I feel like they are where GPUs were 5-10 years ago.
Yeah, actually, I think more years ago, but yeah.
Yeah, they're a bit late on the party for all the reasons you said, but I think it's very interesting to build something around the community there.
Xilinx is the best. I mean, and I don't think they're good, but they're the best. They're the ones who are, I think, most attuned to how to make this better for everybody. They have no interest in doing it for the greater good of humanity or anything like that, but they want. I think they've acknowledged that there are third-party tools and that may do better, and that customers might want to have the ability to debug themselves. So yeah, I'll look into Xilinx tools, but I get all the Altera stuff for free, so it's hard to.
Yes, obviously. Yeah. But it's. I think in a lot of these companies, there's a lot of the enemy is the other company, right? Type of mentality that makes it really hard to. So
Yeah.
I think we need to lead from the outside.
Well, and you know, for me, there's like, and the Intel graphics folks know, like you have this re-education where every time you do something new, you have to explain why it's open source is beneficial, you know, why you're not going to spill all the secrets by opening these things, why documents can help, and I don't know if there's a way to like write this all up and like send bulk letters, but it gets really tiring. I mean, I did it with graphics. I did it with FPGAs. I'm doing it with this new project I'm working on. It's just, I don't know. I wish I could send like just a stock letter and be like, hey, asshole, this is why you should do this. Yeah.
Hi, Ben. Okay, so I could just add a little more to your presentation, and I don't want to pour any kind of cold water over anybody who wants to use FPGA, but a couple of things. One is, most important thing that people have to understand about FPGA industry, because I was an intern at Altera, so I got to see what Altera was like before Intel acquired it. First of all, FPGA vendors kind of thrive on lock-in.
Yes.
Locking in the customer design wins. And then that ensures them about maybe somewhere from 5 to 10 year business, design win. That they will continue to buy the same chip for about 5 to 10 years. Usually they have a much more longer, commitment to the product in, let's say, a GPU industry, which usually they will refresh it every like 1 or 2 year, right? But one of the thing about the lock-in part, and one of the part the FPGA vendors will never, ever open up is the placing route software and the bitstream stuff. They will never, ever open that up, because if they do that, they basically cannot lock in people as easily as they could in the past. So I don't want to say this, but people should not have some kind of really, expectation of that happening anytime soon. Another thing about Lattice Semiconductor, and I hate to kind of trash them, but they are like a low single-digit percentage vendor.
I think
they are irrelevant.
8%, I think they are.
Probably below that. So the industry is really an X versus A. Xilinx versus Altera. It's now Intel, but I still like to call it Altera. So it's either one of those. And also another thing that limits FPGA's kind of growth is what you were showing about the history of the FPGA industry, and it hasn't really grown. As you're correct, they're limited really by how much money comes in. That translates to how many engineers they could hire. The biggest issue they have is really like they don't have enough software engineers to develop their software.
Yeah.
It's not a hardware
Well,
issue.
so one thing I didn't mention, by the way, is there have been several other FPGA vendors who went out of business specifically because they couldn't build an actual credible software stack to run. So they had the hardware and not the software. And so maybe you're right. I mean, maybe Altera and Xilinx aren't the ones who push this forward, but there's, I think there should be a lot of interest in the lower end guys who combined, are 20% of the market.
So last thing I'll add to this is, since I'm more of a hardware FPGA background guy than graphics, I could say this, but I think for graphics software background people, the only way you guys could use FPGA effectively is high-level synthesis. That's it. And high-level synthesis, again, that stuff is all about how much FPGA vendors are willing to invest in hiring people and write all the necessary software stack. Like you have to send the data to the FPGA and do whatever number crunching and send it back to the host, right? That part it's really dependent on how much they're willing to invest in that area. Yeah. Xilinx is maybe I don't mean to say I'm a Xilinx fan, but they seem, I think it's called Vitis. That's the stack they just announced a couple days ago. But they're trying to do that. But as you're correct, high-level synthesis has not really taken off.
No.
So I don't know the reason for that. But and also one last thing is I'm surprised you didn't talk about one API.
It was in one
was
of the
in there.
boxes.
Okay, I missed it.
It
Sorry.
was next to Sickle.
Yeah, and basically, if I were to conclude, what should I say? The only way software people could use FPGAs is through high-level synthesis, I think. Doing the
or
conventional
these
way.
other APIs, right? Like Sickle or one API.
Yeah, conventional way of doing it is like designing like with Verilog is not for the software people.
Well, it depends on what their interests are. I mean, I have trouble doing anything complex, but I find it fascinating. So if you want to spend time, I mean, everybody in this room is smart and they can learn.
But it's a different mentality because I do that
Sure.
stuff and not this stuff. I'm
Sure.
just learning this stuff on the side.
Yeah, but that doesn't mean you're not going to do it because you didn't go to school for it. Hi.
Hi. Yeah, so about what Kevin is talking about with high-level synthesis, for the open source toolchain, there is a pretty credible alternative called MyGen. It's
Yes.
essentially Python.
Yes.
It works. Products are being shipped using it today.
Yeah, they actually use RTL-IL internally. Yeah, but that's a good mention of the project.
So if you want to get into this, that's a good place to start.
Yeah.
Also, the SymbiFlow open source toolchain is it's really the one to use if you're on the lattice FPGAs, but it's also becoming increasingly viable on some Xilinx-based ones, like
Yes.
the Sync ones, and
Yes.
there's the 7 series of FPGAs.
I think it's a 7 series, yes.
It's
And
not-
even for Altera, you can, what currently works is you can get a VQM, so it's like an input file into the Quartus toolchain. So you can do the synthesis in Yosis, and then you can do the rest in Quartus.
The rate of progress in this space is kind of staggering. Like, they're making such good progress, and it really feels like the GPU space 10 years ago, just like you said.
Yeah. Well,
Um,
hopefully people will go and make things better. I hope.
And if you look at the performance of the lattice-based toolchain, there are cases where you can, for example, synthesize a RISC-V CPU, and it'll occupy like 90%, 95% of the FPGA on the proprietary toolchain, but only like 35 on the open source one.
I have data which I'm not allowed to show because the end user license agreement for Diamond doesn't let you show it, but I did compile some data comparing both Fmax and area and yeah, generally the Yosis, I guess symbiosis is the right word, although I think that's mostly for the formal verification flows, but they definitely don't win most of the time in terms of area or frequency. The synthesis time is definitely better, and I did find a few designs that are like remarkably better with Yosis. So it's not like all bad, which was great news, and that was part of my presentation to the internal people of why I think we should support Altera better with open tools. But yeah, I don't know. Not my pay grade to make that decision, unfortunately.
Cool. Yeah. Thanks anyway for talking.
Yeah,
about this
thank
stuff.
you for bringing it. Yeah. Okay, thanks everyone.